My name is Jeff S., and I'm here to talk about knowledge transfer. That is, teaching. You can't download a brain, unfortunately. We have to go through the mechanisms of our human cognition. Now, we don't really know how our brains work, but we still try to figure it out, and there have been several theories proposed to try to describe the processes and mechanisms that happen with cognition and learning. One of them is called cognitive load theory. And to kind of simplify, this theory describes three loads on our cognition. There's an intrinsic load, which describes the energy going into learning the actual material. Then there's an extraneous load, which is caused by distractions or poor instructional design. And then what's left over is the germane load. This is the energy for actually learning. The extraneous load distracts from the germane load and should try to be minimized. Another theory is the cognitive theory of multimedia learning, which also tries to describe the processes that go on in our brains. But what's different here is the multimedia part of the name. We use vision and hearing simultaneously and synergistically to learn information. A temporary kind of working memory in the middle takes input from our senses, processes it, selects it, organizes it, so that it can be stored in our long-term memory. And so some good design of learning activities takes advantage of these dual channels, vision and audition. There are a lot of differences between these two theories, but there's also some similarities, in particular this concept of what's extraneous. Let's take a look at some of the principles that are informed by these theories and how they can apply to your instructional design. For example, let's say that we're talking about a dog and these things called ears. And if I were to describe on this picture, look at the dog's head. You'll be able to identify the head by the eyes. On the side of the head are these floppy kind of things. These are ears. As you're listening to me speak, you're also looking at the picture and trying to synchronize and resolve those two. But let's try it a different way. A dog has ears on its head, and these are used for hearing. All right, so much simpler. The arrows draw your attention to the items in question, so you can focus all of your intrinsic load on learning what the ears are and minimize the distractions of the extraneous parts of the dog. Another principle informed by these theories is the spatial contiguity principle. Related items should be together. In this picture, we see two puzzle pieces, and the idea here is that, for example, if there's a picture on one page and the explanation on another page, the learner has to flip back and forth to try to keep all of that synchronized. This adds to the intrinsic load, trying to visually remember and process the picture, but then also keep that floating while you flip pages and process the words. By having related items together, this makes it easier for the learner, minimizing that extraneous load. Another principle is the temporal contiguity principle. By having visual presentation synchronized with spoken or verbal information, the learner can take advantage of this dual channel input processing and the synergies that are afforded to help reinforce the learning, synchronize the auditory and the textual parts of a presentation so that the learner can take advantage of these dual channels. And these principles and cognitive theories are fine as far as they go. They can really help design with the principles that I just mentioned and many, many more. But there's a different kind of way to approach this because humans are not flowcharts like this. So how can we take advantage of the prior knowledge, the prior experiences that students invariably bring to class? The understanding they might have could be informed from their parents, or it's just accepted common knowledge, and it's not always correct. Further, science and technology continue to advance, and what may have been known to be true decades ago, it just isn't anymore. And so it's helpful to have refutations in certain types of learning activities, to be able to say to a learner that you might think this is what happens, but it's not true. Instead, this is our current understanding. You acknowledge and even describe the misconception, and then say in plain English, no doubts, this is not true. And this puts a learner in sort of a mindset to say, okay, I know this old one, but the teacher's telling me it's not true. What's going on? You go into your explanation and refutation about that misconception. This has nothing to do with the cognitive theories, but it does also acknowledge how learners come to class. Let's take a look at how these principles can be applied in an actual lesson. Are you ready to learn about computer networking? Computer networking is complicated. You see, computers don't just talk to each other. There's a whole set of interconnected technologies that enable communication. Look at this picture and imagine each ray of light being a network connection. Some span the continent, some wrap around to the other side of the world. Imagine building a computer network the size of a planet. You might think that your computer or your phone or your Xbox, it has an IP address, and this enables the communication. And that's not wrong, but it's woefully incomplete. You'll need a lot of study to learn all the technology that makes this work. Think about, maybe you know this person. As soon as something goes wrong with their computer, they can't get their email, and they say, oh my gosh, the internet is down. Have you heard that person? Do you know, maybe you are that person? Well, think about it. If the internet is down, we need to prepare for an apocalypse, all right? Now, what's more likely is that there's some piece of the puzzle that's broken for that one particular person. It's not the entire internet that's down. If you want to diagnose and fix those problems, here's a way to work with that. Technologists use what's called the OSI network model. This describes networking in layers. A stack of layers. Each layer has its own responsibility, and each layer only communicates with the layer above or below. And by handing off responsibility to the different layers, we allow a network to grow the size of our world. And you can even start to see some of this even if you don't understand a lot about networking. For example, at the top here is what we call the application layer. This is your email program or your Netflix. And then here at the bottom is what's called the physical layer. And this could be a wired connection that you plug into the wall. It could be wireless. It could be dial-up internet. Do you remember that? These two layers are very far apart, and they don't concern themselves with each other. For example, you can get your Netflix on a wired connection or a wireless connection. Netflix doesn't care. It doesn't know. On the other hand, the physical layer doesn't know what kind of information it's transmitting. Pulses of electricity on a network wire could be Netflix, could be email, could be hilarious cat videos. Who knows? Pulses of light on a fiber optic cable, again, it's just ones and zeros, and we don't know if it's cat videos or email messages. The physical layer and the application layer are totally separate, and this allows us to swap one for the other. And there's other layers in between, but that's the principle of layers. Each layer has a responsibility and talks to the layer above or below. So let's dig a little deeper. At the bottom of the stack here is the physical layer. This is how one computer connects to another. Could be a network cable or could be wireless. And then through that cable, through that medium, then pulses of energy or information are sent that go to the destination. A little bit higher up is what's called the data link layer, and this is how information is put on that cable. Fiber optic cable uses pulses of light. Wireless cable uses radio transmissions. Wired cable uses pulses of electricity on a copper wire. How that gets encoded on that medium, the fiber optic, the copper, the air around us, is handled by the data link layer. Up above that then is the network layer, and this is responsible for getting information from one place to another, even if that other place is the next continent or even just the next town. This is where that principle of the IP addresses comes in. This is necessary, but it's not sufficient. Next up is the transport layer. Transport is responsible for packaging large units of information and dividing it into smaller. We send these things called packets, chunks of information. So that hilarious cat video might be 3 minutes long. It gets chopped up into these little chunks and sent one by one, and the transport layer organizes sending them, and then at the receiving end reassembling them so you can watch that cat video. And then we go up a little bit higher, and then we have a session layer. And think about this, you're using your laptop and you're watching Netflix and you're reading your email and you're messaging your friends and you're downloading the hot new video game on Steam. All these network things are happening. How does your computer keep track of which information is email and which information is Steam? This is handled by the session layer. The presentation layer, this one's a little hand-wavy, doesn't really show up in real-world networks, but the idea is presentation translates from one format to another. So for example, let's say you want to send an email message to your friend and you want it to be super secret so that if it gets intercepted in transmission, nobody else can read it. Well, through the power of mathematics, we can do what's called encryption to transform the original message into something that nobody else can read. That would be the responsibility of a presentation layer. And then finally is the application layer. This is what you're most familiar with. You've got your email program, your Netflix, your Steam downloads. All these things are running on your computer. This is what you, the user, interact with. And so you can start to see then with these layers how it all works together. At the application end, you've got your email and your Netflix and your hilarious cat videos, which hands off information to the presentation layer for transforming somehow, to the session layer, to the transport layer to divide into chunks, to the network layer to deliver to the destination, and so on till the physical layer sends pulses of information along a medium, a cable or through wireless. And then at the other end, the information gets received and the process is reversed through all the layers until at the very top, the corresponding application at the other end can view that information. So you send an email message, you hit send, information descends through the layers, and then the recipient, the reverse process happens up to the top of the layers for your recipient's corresponding application. So, how did that go? Do you understand that networking is complicated? When that person says, oh no, the internet is down, well, you can see there's a lot of parts, and if any one of those goes wrong, well, then they're not going to have a connection, but it's not very likely it's the whole of the internet. And so it's up to you as a technology professional to understand this concept of the layers and how they apply to our computer networks to help you figure out where the problem actually is. You could make a profitable career out of installing and troubleshooting and maintaining computer networks. So, there's your lesson. I used refutation to say that previous notions are probably incomplete, if not outright wrong. I used signaling to highlight the different parts of my diagram. I used spatial contiguity. My presence and my visual aids are right next to each other in the same video. I used temporal contiguity. My speaking is synchronized with what's happening on the picture here. And these are all informed by these cognitive theories that I've talked about. And as instructional designers and teachers and professors, we need to be aware of how we can use these to make our classes better and to improve our students' learning outcomes. I hope this has been helpful, and I hope I'll see you on the internet.